So, hello everyone. My name is Costa Kapsis. I'm the TC6.7 on Solar Energy and Other Renewables Technical Committee on ASHRAE. I am the current chair, and I'm delighted to have Professor Janice today with us to talk about climate change. We will be discussing more about Janice's presentation, so we're delighted and honored to have you here, Professor Means. But before we move into that, I would like to mention that for our participants, if you wish to join our TC6.7, I'll be dropping a link on the site that you're more than welcome to register and participate actively in our activities as technical committee on solar energy and other renewables. Also, we have two upcoming technical committee meetings during the Chicago meeting that will take place in Chicago, Illinois, in January 20 to 24th. Our first meeting is going to be subcommittees meeting on January 20th, Saturday, 1 to 5 o'clock local time. And the following one is going to be on Monday, January 22nd. That is going to be our general meeting. You're welcome to join us in person if you're going to be in Chicago attending the conference, or also online. Typically, our meetings are hybrid. Without further ado, I would like to pass the microphone to our outreach chair, Ana Maria Segunis from Concordia University, to make the introductions for our first speaker today. And Professor Means, on behalf of TC6.7, thank you for being here with us. And Ana Maria, the microphone is yours.
Hello, hi everyone. So I'm happy to welcome you at our first TC6.7 webinar. So as Costa mentioned, we have the pleasure today to have as our first guest speaker, Janice Means, a professor emerita at Lawrence Technological University. Professor Means is an ASHRAE Fellow and Life Member and is currently serving as the ASHRAE TC 2.5 Handbook Chair, editing the Handbook of Fundamentals Climate Change chapter. She is a voting member of TC 2.5 on global climate change, of TC 2.8 in building environmental impact and sustainability, and is also a past chair of our TC 6.7 on solar and other renewable energies. So today, Professor Means will be talking to us about the causes of climate change, its global effects, and will present a USA case study for the state of Michigan. If you have questions during the presentation, please leave them in the chat, and also please refer to the slide number so our speakers or Professor Means can easily access the slide that you are referring to and answer your questions. So yeah, without further ado, I would like to give the floor to Professor Means.
Thank you, Ana Maria. And welcome, everyone. I'm going to be discussing climate change and climate crisis. And the slides are not moving. There we go. Sometimes there's a little bit of a delay. So the learning objectives for this presentation are as follows. It's being very slow, Costa, there. After following this presentation, you should be able to describe how current global change, climate change, differs from natural cycles. Contrast the difference between weather and climate change because they are different. Explain the role of volcanoes, if any. Lists 4 changes the world is experiencing today due to climate change, because we're in climate change right now. And we're going to also, you will also learn about the isotopes of carbon and how they can be used to determine where the CO2 is coming from. And finally, I will be really defining mitigation, adaptation, and providing resilience. And you should be able to come up with some examples of each afterward. I want to start with some thank yous and acknowledgements. First to ASHRAE Technical Committee 6.7, Solar and Other Renewable Energies, for sponsoring this webinar series. And in particular, I'd like to thank Costa Kapsis for hosting this, along with his employer, the University of Waterloo, as well as Ana Maria Segunis, who helped in the publicizing of this event. I also should add that Kostas Balearis of Greece and Khaled Negedi of New York and I had initially conceived the idea of sponsoring this webinar series. Also, I have to thank and show my gratitude to the climatologists from whom I've learned so much when I worked on the ASHRAE Fundamentals Global Climate Change chapter. So let's get started. Today I'll start with a brief introduction and then go into spending a lot of time actually on answering the question, is today's climate change anthropogenic? In other words, is it human caused? I then will present some key potential and present future present and future potential future climate outcomes. And I do this globally and then come down on a short case study that goes from the United States and on to the state of Michigan. I then describe mitigation, adaptation, and resilience, and then I have some concluding remarks. So let's start with this introduction. Why is climate change literacy important? Well, first of all, it's an existential threat. It's not something in existential threat. We are actually in climate change now. It's not something in the future. Since 1960, some of you may be surprised to learn that temperatures have increased 100 times faster than any natural cycle following an ice age in the last 800,000 years. And I believe that we need to spread the knowledge in order that we can get action taken on addressing climate change mitigation and adaptation. ASHRAE, in the position document, has stated very clearly, and I'm going to read the quote, climate change is the most formidable environmental challenge ever faced by society. So it's important, in my view, and in ASHRAE's, for you to understand what it's all about. So climate change is different from weather. Weather is the day-to-day changes. The day-to-day, even year-to-year changes in temperature, humidity, storms, basically. But climate change is different. And we're going to look at the United Nations Intergovernmental Panel on Climate Change, the IPCC's definition to understand this more fully. It says, quote, a change in the state of the climate that's identified by changes in the mean or variability of its properties. And note this last part, persists for an extended period. And that's typically decades or longer. So what role or how does global warming fit into climate change? Well, global warming, of course, is going to happen when the solar radiation, because the sun is our source of heat and energy, even some of it that we've stored. But when the solar radiation reaching the Earth exceeds that it's leaving, we get what's called global warming. And there are certain greenhouse gases that act very much like glazing on a greenhouse, and that's why they're called greenhouse gases. What happens with glazing, you have shortwave radiation coming in as light that travels through the glass, and once it turns into heat, which is long wave radiation, it's bounced back basically by the glass. Well, greenhouse gases kind of act like this. So that's why they're called greenhouse gases. So let's look at radiative balance and imbalance contributors. There are many natural and human drivers of climate change. And basically, greenhouse gases lead to global heating. So what are the greenhouse gases? They're actually water vapor, carbon dioxide, methane, nitrous oxide, and ozone. And you may have noticed that others have said, well, why aren't we spending more time on water vapor? Because that has the most influence on it. Well, the reason is water vapor changes very rapidly and recycles itself. And when we have warmer temperatures around the Earth, more water vapor goes into the atmosphere. So scientists think of it as more of a feedback or a forcing factor than an actual contributor. We also have cooling, and this happens when the sun's light is reflected by, say, volcanic ash, snow, clouds, etc. So when these are unequal, we get a radiative imbalance. And when the first is larger than the second, of course, we get global warming. So what is the cause of the currently observed global warming? Is it anthropogenic? In other words, is it caused by people? So it's thought that the most important significant input is human caused, mostly with carbon dioxide, methane, nitrous oxide, and ozone. And this is due to land changes, landform changes, the deforestation, the burning of fossil fuels, which provides our transportation, it supplies our buildings with energy and our industries and all the processes we use. Agricultural changes, and then also which contribute to the nitrous oxide, as well as the significant amount of food that most of us, at least in the Western world, eat, which is cows and sheep. Now, cows and sheep are ruminators, and they expel a lot of methane. There's also some ozone that is coming from our fluoridated glasses. And notice I have left chlorofluorocarbons off because they aren't such good as much contributing to the climate change as these two are. So is this actually the case? What evidence we have? And I'm playing sort of devil's advocate on here. So is climate change caused by natural forces? Well, let's look at solar activity. Now, on this chart, which starts in 1880 on the x-axis to 2020, the y-axis on the left side is the total solar irradiance, which is in yellow, and you can actually see the radiance, and it varies. The 11-year average is shown on a darker yellow line. On the right-hand y-axis, we have the degrees in change in degrees centigrade or centigrade degrees, and that's in red. And again, you can see how this varies, but then the 11-year average is shown in red. Now, if you look at 1960, you'll see that there is a relatively close relationship between the solar irradiation and the temperature increase. So I could see how people could think that that was the cause. But after 1960, the solar irradiation has decreased, but our temperature difference has, our temperature has increased greatly. So it's not solar activity. So is it caused by volcanoes? You'll hear a lot of people say, oh, volcanoes give a lot of CO2. Well, let's look at what volcanoes give out. And I've got a little cheat sheet here on chemical formula for those of you that aren't strong in chemistry. And it helps me too, since I'm not a chemical engineer. You have carbon dioxide being given off, and depending on the type of volcanic eruption, we may have a lot of ash, hydrochloric acid, which comes down as acid rain. We have sulfur dioxide, which reacts chemically with the hydrogen to create sulfuric acid. And these combine to actually increase the albedo, or the reflection of the sunlight. Okay, and there's some other processes going on. By the way, I will be mentioning the troposphere and the stratosphere later. So notice that the troposphere is pretty much where almost all our weather takes place, and the stratosphere is a little bit higher. Actually, the troposphere runs from 0 to 10 miles, and it depends on where you are in the world on how high it is. And the troposphere, or excuse me, the stratosphere is 10 to 31 miles from the Earth. Okay, so we can definitely say particulate and SO2 emissions provide a cooling effect. And when we look at the carbon dioxide, it's not just the fact that the volcanoes are giving off carbon dioxide. We have to look at the amount of carbon dioxide they're giving and relative to that of what we think are caused by human activities. And it turns out it's less than 1% that's emitted by all volcanoes, both on land and undersea or submarine volcanoes. So there's been some question as to what about these submarine or underwater volcanoes? Are they warming the ocean, which is causing climate change? Well, scientists have recently found that there are a lot more submarine volcanoes than they thought there were. Okay, the ocean is very unknown. It's sort of more, we probably know more about our solar system in some respects than we do about our own planet's ocean. But even though they're discovering more about these, notice there's no evidence that they're becoming more active than they were before. And if you think about it, with the volcano coming from under, you would think that it would warm water from the base, wherever height it comes in the ocean, up to the top. But most of the surface water is what's heating up, and it's colder as you go deeper. They're stratified. So, but what about the unique Hunga Tonga Hunga Hapai January 22 eruption? And I dare you to say that 5 times without slipping over it. This eruption was rather strange. It produced a tremendous amount of water. I've cited one of the technical research papers on this, and I have a quote from it. The short wave heating and long wave cooling by aerosols appear to roughly cancel. Now, again, this is very unusual. It ejected more water into the stratosphere than ever's been recorded. It was 10 to 15% increase in water. But the thing is, water vapor dissipates quickly, okay, in the hydronic cycle. But CO2, carbon dioxide, stays in the atmosphere from, a couple of years to hundreds of years, maybe even 1,000 years, depending on the different inputs. But one thing that was that the Hunga Tonga Hunga Hapai eruption did do is it resulted in opening the ozone hole over the Antarctic, which is about the 12th largest it has been. So let's look at the plot of temperature rise, and you're going to see this particular chart again a little bit later, but let's look at that and look at volcanic eruptions. This chart this graph goes from 1880 to 2020, and it shows temperature anomalies in degrees Fahrenheit. Okay, so let's look at these dips. This first dip happens to coincide with the 1883 Krakatoa eruption in the South Pacific. If we then look at this really big dip, it corresponds to the 1912 Novarupta eruption in Alaska. Note that this eruption was the largest ever recorded in the 20th century, and it did look like it had a big impact on cooling the environment. And notice these only last for a couple of years. They're not permanent cooling. The 1943 to 1952 Periatan eruption in Mexico, and again, it was extended and this flattens out a bit here. The 1969 to 1974 Kilauea, Hawaii eruption. And by the way, some of these don't put as much, or even ones that are erupting several times, they don't always put as much into the atmosphere. They might put more lava out on the ground, for example. Mount St. Helens, which some of you will remember, was 1980. And again, we had the cooling following that. And Mount Pinatubo in the Philippines, 1991, again, we have it leveling off. It didn't seem to have as big an impact. And then in 2010, and I'm going to butcher this name, but bear with me, the ASHRAE eruption in Iceland. And I particularly remember this one because I was presenting in Turkey at the time this was erupting at a Klima 2010 conference. And I had the last plane out before they were going to stop flying again because of the particles in the air and disrupting the flying. Okay, so you can see all along here that volcanoes provide some short-term cooling, or else who knows how high temperature we would be at. We'll be coming back to that chart in a moment. So some say, okay, there's a normal natural cycle that's causing this, and there is something called the Milanovich cycle, which has to do with changes in the path of the orbit the Earth takes around the Earth, and also the wobble of the axis of the Earth. Okay, and they attribute these to the reason that we have ice ages. On the left here, this chart starts 800,000 years ago and goes to the present. We have temperature change listed on the left, which is shown in the lighter blue. And on the right y-axis, we have the carbon dioxide in parts per million, and that's shown in the dark blue. And you can see that these pretty well track. You also can count the 8 ice ages that we've had. Okay, and there's, even though it varies from ice age to ice age, there's a pretty much a strong path about how they increase and decrease. And you can see that it looks like we should be right now ready to go into a cooling stage. Okay, let's compare this chart to a similar one, which plots the global mean sea level. This is starting 771,000 years ago, which is pretty close to 800,000 to the present. And I think if you take this chart, if you could impose it on the other, you will see that they pretty well track. So here what we're finding is that CO2, temperature, and global mean sea level are very closely related. Okay. I also might mention when we talk about natural cycles, there is some temporary cycles that take place, the La Nina and the El Nino, which causes temporary heating or cooling throughout the year. And right now we're in an El Nino, which means it is having some effect on increasing temperature. But again, those are temporary. Okay, let's talk CO2 levels. Now, depending where you measure the CO2 level and the time of year, you're going to find some differences. And if we looked at North America, for example, in the winter time, and the closest I could get one recent was in October, so it's starting to get cooler, it had a recording of 400 and almost 420 parts per million. But this summer, the parts per million were larger, 400 and over 423 parts per million. Why is that? Well, if you think about it, when northern hemisphere is in winter, the southern hemisphere is in summer, and that's when things like the Amazon rainforest will be able to absorb more of the CO2, whereas our summer, their winter, they're not going to be able to absorb as much. So that's why it goes up, at least from where these readings were taken. All right, let's look at that other chart, but I'll elaborate on it a little bit. Going back again, 800,000 years to present. And by the way, they can tell these by taking ice cores, for example, and looking at geological readings in rocks. Okay, so on the left, we have, again, the parts per million for the y-axis, and I've already mentioned the x-axis, and here we have the path that's taken. Notice that nowhere in time from 800,000 years ago has the parts per million gone above 300. And in most of these, it has not exceeded 280 parts per million. But in 1911, the parts per million increased to 300, okay? And it's been going up exponentially ever since. Since the mid-1900s, it has gone up 10 times faster. And this is also with, well, temperature and the CO2. And it's 100 times faster if we look from 1960, again, compared to the natural ends. And again, look at this. It looks like we should be starting back down. Even if we went up here, being at the highest point it had been before, we should be going into a cooling stage, but we're not. May 9th was the first time that 400 parts per million were exceeded. And again, this looks back even further. It's the highest in 3 million years of Earth's history, is the most likely. So we've gone from 1911 to 2013, which is about 100 years, and we've increased, or there has been an increase of 100 parts per million of CO2, when again, originally it stayed under 300 total. Okay, so let's talk about global mean sea level and also temperature records and well, I guess we have already talked about the CO2 temperature records and mean sea level, but I brought this slide in because I want to make you aware of climatelevel's.org. Again, that's climatelevel's.org, because it's kind of a nifty site in that you can look at a lot more than these three, but you can check, print, or excuse me, click on a point and actually get a reading for that particular date. So again, all of these are going up exponentially. Okay, we're back to that original chart. We're going to look at this in a little bit greater detail. So since 1980, we've had unprecedented warming and increase in CO2, which I've already talked about, 10% faster than the average rate, warming, falling, an ice age. As of the AR6 synthesis report by the IPCC, we have they had indicated that we had about 1.1 degrees Celsius or 2 Fahrenheit degrees higher in the period 2011 to 2020 compared to the 1815 to 1900. By the way, these numbers go up and down just like the CO2, and but we're still headed up. Okay, so if you check today, at least the last time I had checked, it was a little bit lower than 1.1 centigrade degrees or 2 Fahrenheit degrees. So don't hold me to that. That's what I was recording from the IPCC report. All right, I have added a box here because the fastest warming has occurred since 1960, and you can kind of see how this is, it's not level, but it's not at a high rate from 1880 to 1960. 1960, it really picks up. So the fastest warming has included the hottest years. In fact, the hottest years have occurred just in this last decade from 2010. And they had 2016 was tied with 2020 as being the hottest year ever globally. And this is probably no surprise to most of you, there's a very good chance that 2023 will be the hottest year. Or another way to look at it, it may be the coolest year from this point further, which is kind of scary. Okay, let's look at human and natural influences on global temperature. And if we look at models, and models aren't precise, okay, they vary. So you're going to see some variance in results from models, but we also look at what the average is. So let's look at this. Going from 1880 to 2020 on the x-axis, so time, and then looking at temperature difference, this time on this chart it's degrees Fahrenheit. We can first look at the blue. And again, you can see it varies, but here's the average, okay? blue. And then we look at, again, that is for natural drivers. And then we look at human drivers. The human drivers are in red. And if we look at the combination of the human and the red, we get the yellow drivers. And when we compare that to which actually has been observed, which is in the black, you see that there is a correlation. So observed global temperatures are much higher than the Earth would have experienced had we not had human influence on these. Okay, let's talk about carbon isotopes. And this is what really sold me on believing that climate change was caused by fossil fuel use. Okay, so let's talk about, again, carbon. Carbon has an atomic weight of 12, which means it has 6 protons and 6 neutrons in its nucleus. Now, they do have isotopes of carbon-13, which has an extra neutron, and carbon-14, which has extra 2 neutrons. Now, we all are familiar with carbon-14 dating because carbon-14 is radioactive and it loses particles through time. But fossil fuels are just that, fossil fuels. They're very old, and any of the C14 in it and most of the C13 would have dissipated and left by the time that we started using them. So keep that in mind, and then look at how CO2 levels have increased. They're 40% higher in 2019 than in the 19th century, and 50% higher today in the 19th century. So when we look at the current concentration of carbon isotopes, we find that the C14 and the C13 have significantly decreased in the fraction of the total, which means that if we have most of the fossil fuel carbon coming in, it's going to dilute that value. So it means that fossil fuels really have created more CO2. All right, let's look at the IPCC 6th assessment report and their later synthesis report, which is also part of the AR6. They have stated, quote, "It is unequivocal that human influence has warmed the atmosphere, ocean, and land." And they didn't come by this overnight. If you look from their reports from 1990 onward, they were very careful to analyze everything before they had made this statement. Additional to that, and this is only a partial list, worldwide scientific societies believe and have stated that climate change has been caused by human action. And there's even data to show that the oil and gas companies knew this years ago from studies that they were done. So I hope I have convinced you, if you weren't convinced earlier, that climate change is due primarily to human action. So let's move on to the next section and look at key present and potential future climatic outcomes. So first of all, everything is happening at an alarming rate, and it's much faster than was ever predicted on there. Again, global temperature has increased drastically by about 2 Fahrenheit degrees or 1.1 centigrade degrees just since the industrial age started. Climate zones are on the move, and I thank Michael Roth, who's also an ASHRAE member, for sharing this with me. This chart shows in color the different climate zones. I'm just doing it for North America for this example. By the way, climate zone 0 is a new climate zone. It was added because the temperatures were getting so much hotter. And you can see where climate zone O is right here. Well, in any case, each one of these climate zones that have little white dots shows where the climate zone has moved up a zone. And this is equates to about 100 miles north. And it does vary on where you're located on how this happens, but we're definitely getting hotter. So there's also, if we look worldwide at temperature anomalies from 1900 through basically to 1940, we only had extremes, low record lows. Then we started getting a little bit pick up in 1940, but then when we get to 1960, we start seeing more and more record highs and fewer record lows. In the 1970s, we're only getting record highs. By the way, the green and yellow shown here are just two different ways to measure the satellite data, but they pretty much track. So this also shows that our climate worldwide is getting hotter. What does this cause? Well, Arctic sea ice is decreasing rapidly. It's down 12.2% when compared to 81 to the 2010 period. So we're looking at this right here is down to 12.2%. If we look at 1980 right here, and we can read that value, it's 7.54 million square kilometers of sea ice, or 186 trillion acres. For 2022, it's down further to 4.67 million square kilometers, 1.15 trillion acres. And in 2023, it's 4.37 million million square kilometers, 1.08 trillion acres. Now, again, this goes up and down, just like so many natural processes, but you can see how it's on a rapid decline. Glaciers worldwide, again, are also disappearing or at least shrinking. And what is this effect? And I'll get in this greater detail in just a moment, but it raises sea level, okay? It makes it harder for people to get water, people that are dependent on that glacier water coming down for their livelihood. It affects hydroelectric plants when there's not enough water to go through to generate electricity. And it affects safety. For example, in parts of Switzerland where the glaciers are melting, the mountains are coming down. They're literally falling down on these villages. I first went to the Columbia ice fields in 1975 when I was driving the Alcan Highway. The second time I went, my late husband was driving. He pulled in and he said, "We're at the Columbia ice fields." This is 1988. And I said, "No, we're not." It had looked so drastically different to me. It had receded so much. I went there again in 2017 and could see that it had even receded further. But they also had some of these signs up, which I thought were interesting. In 1919, you can see the mouth of the glacier coming out here compared to a time, I'm assuming it's around 2015, 2016, and you can see it's greatly reduced. And what also this does, when the ice melts, it exposes darker ground, which heats up from the sun more, and it just accelerates. Also, the Mendenhall Glacier. These are satellite photos that are enhanced in color, and the red, or excuse me, red, the blue, light blue actually shows the glaciers, and the dark blue shows liquid water. This is first one on the left is from 1984, and on the right it's from 2023. I was there in the early 2000s, and I was at the visitor center, which is close right to this Mendenhall Lake, and you could see a video showing how rapidly things were changing in the glacier, how it was receding. But what I found really remarkable is that they had a blackboard, which daily they were noting the changes in the glacier. So it's greatly receding. Sea levels are rising as a consequence of the glacial and sea ice melting. And also part of the reason that they are expanding, or excuse me, are rising is because of the expansion of water as it heats up. The ocean is heating up. Ocean stores a lot of our carbon dioxide, by the way. The global mean sea level has averaged 21 to 24 centimeters or 8 to 9 inches since 1980. In 22, it rose 10.12 centimeters, 4 inches above the 1993 levels. So it is rising very quickly. And a lot of island nations and even large nations are having problems, especially with storm surges, because even though it, excuse me, the sea rise hasn't been that great, when you have a storm surge, you're more likely to have flooding. And this is happening, for example, in New York City and other places. It's likely to rise 0.3 meters to 2 meters, 1 to 6.6 feet above the year 2000 levels by the year 2100. And if you look at some of the models, the pathways, as the IPCC calls them, we can have much, much greater sea rise than that. And for those of you that are interested, I want to show you how to get to a tool. It's called the NASA Sea Level Projection Tool. If you just it's sealevel.nasa.gov, but if you just look at, or excuse me, do a search on NASA Sea Level Projection Tool, you can get into this. It goes through looking at different projective pathways, and you can click on a particular location and get more information on what they're predicting should happen with the sea level. Okay, extreme weather events. And some of you say, okay, it's weather, but I've been teaching global climate change and sustainability for over 20 years. And I had talked to my students about weather events changing and becoming more intense and more frequent. And they certainly have. Wildfires, floods, hurricanes, and more. We've had more frequent heat waves. Summer 2023 was the hottest in the US since records began in 1880. It was the 8th hottest in Europe. And we've had severe heat waves in several places across the world. I thought it was particularly telling that the news reported this past summer that water in the Atlantic near the Florida coast has exceeded 100 degrees Fahrenheit or 38 degrees Celsius in temperature. I thought, oh my. There's extreme rainfall and flooding, again, through several parts of the world. Drought in several parts of the world. And by the way, Somalia has been in drought for a while. It was just on the news this last week that they are now having severe floods. There's record deadly wildfires. I'm sure all of you have heard about the ones in Canada and Hawaii. You might not, if you're American, for example, you might not have known that they also were occurring in Southern Europe, Indonesia, and the US. And these wildfires not only affect the particular area that they're in, they also affect people even hundreds of miles away. For example, I know this summer, before I go out, besides looking at the ozone level and the temperature and humidity, I also looked to see what the pollution was due to the wildfires. Okay, all of these events are very expensive. And if we look at 1922, at just a few of the events, we can get some value or some numbers here. The Hurricane Ian, which have primarily affected Cuba and the US, amounted to $113 billion, that's with a B, $billion. The China floods were a little over $12 billion. China had drought as well as Southwestern and European, and in China it was up more than 8 billion. In Southwestern US it was about $22 billion, and the European drought was exceeded 20 billion also. So they're expensive. So climate change has serious effects, and it affects people in different ways. It affects our environment. We're getting to a point where we're having food insecurity, actually, poor health, and biodiversity. All of these are threatened by climate change, and it's in process now. It's not just in the future. Who's the most vulnerable? The very young, the elderly, the poor, and especially minority and indigenous populations are more affected. Poor nations who most always did not contribute mostly to this problem with CO2, but they are the ones probably most affected by it and with the least likely having the means to do the necessary adaptation to protect themselves. So let's get to the case study, key present and potential future climatic outcomes. But before I get into the case study, I want to share with you that you can try doing your own case study. I was able to find a few sources outside the US, or that cover areas outside the US. One is Canada Climatic Atlas, Australia, the Climate Information Projection Tools, European Union, Europe's Changing Climate Hazards, an index-based interactive EEA report. And by the way, if anybody knows of any others, I would really appreciate if you would email me and let me know, because I'd like to keep track of this. Thank you. So let's look at the United States, and let's look first at extreme climate events. Now, the United States logs those climate events that exceed, for a single event, $1 billion, okay? Since 1980, when they started logging these, through November 8th of this year, there have been 373 weather and climate disasters. Over 16,000 people have died. Over 16,000 people have died for these events. The cost for these 373 events was over $2.645 trillion. That's with a T, trillion dollars. Every state has had at least one of these events. Texas has more than anybody else. There, nearly half of the total events have been in Texas. By the way, if you look at the United States, Texas, Louisiana, and Florida have the most billion-dollar weather events. They're followed, but not closely, by California and New York. Let's look at the average for these. The average number that occurred since 1980 is 8.1. The average per year, 8.1. But if we look at the 4-year period just between 2018 and 2022, it's 18 per year average just in these last 4 years. So they're increasing. Let's look at the state of Michigan. Now, this is a rather complicated chart. I'll start by saying that there were 53 total events exceeding $1 billion per event between 1980 and the date I gave earlier for 2023. This chart starts in 1980, because again, that's when they started logging these events, and goes through our present time. The number of events is recorded on the left y-axis, and it's shown where you have these flat or rectangular numbers. For example, here there were 2 events. The right side shows the cost in $1 billion, and if you look at the brown pointy values here, we can see that these show the cost. So I've color-coded this, or showed the color codes for it, so you can tell what the events are. There were 36 total severe storms, and these are all in the green, and you can count them: 1, 2, 3, 4, etc. All of them. From Michigan, that's the greatest that we get. We get lots, or we are getting increasing numbers of severe storms, and severe storms cause damage. 6 due to, goes without saying, 6 due to winter storms, and the winter storms are shown in the purple. Okay, 5 due to drought, and that's in the brown. And yes, Michigan, even though you'll see it's getting more humid, it has had drought. 5 due to flooding, this is in the dark blue, you can count them. 1 due to crop freeze, which occurred actually in the 80s, and 1 death. So let's look at temperature change. If we look at the entire United States, you can see that the majority of the United States has increased in temperature. The lighter pink shows through the bright red or dark burgundy red, I guess you'd call it, shows the changes. And in Michigan, it's increased more than the global average. I've moved a part of the chart up here, or the key, so that you can see that in parts of Michigan, the temperature looks like it's exceeded 3.5, maybe might even be 4 degrees, but let's go with the 3.5, which is higher than the average of 2. And what's projected is that temperatures will increase even more. Again, looking in that same part of Michigan, the northwestern part of the lower peninsula, well, even in the upper peninsula. In fact, the upper peninsula, it's even increasing more. By mid-century, it's thought that it'll be increasing by 5 or more degrees. It's a lot. So let's look at precipitation. And the Midwest of the U.S. and the Northwest are all increasing in precipitation. Again, some of the values in Michigan right here are showing 20 to 30% more precipitation when compared to 1901. And let's look, what does that increased precipitation cause? Well, it already is causing problems for the Great Lakes and our waterways, because when we have so much precipitation, especially when it's a heavy precipitation, it causes flooding, and the sewage systems can't handle it, and the sewage then gets dumped into the waterways. It's causing increasing erosion and also algae plumes. The algae plumes, again, cause health issues. It's dangerous. It's causing flooding and disrupting of transportation networks and other infrastructure. For example, when the storms go through, which is usually accompanied by heavy rains, we have electrical lines going down. It's negatively affecting agriculture as well. You can't plant in a field that's flooded, for example. And I've already mentioned it's increasing human health issues. One positive thing is we have a lot of trees in Michigan, a lot of forest. It may decrease the threats of wildfires because of the water. By mid-century, the projected average precipitation difference in inches is increasing throughout the Midwest, but in the in Michigan, again, from 2.4 to probably about 4 inches. Sorry, I haven't converted those to metric units. The mid-century difference in the number of days of heavy precipitation. Wow, look at this. It's increasing for everywhere, but especially in the upper peninsula and the upper northern part of the lower peninsula, as well as around the Detroit area and Metro Detroit area. The number of days increasing as much as over 1.5. So in summary, on this case study for Michigan, because of this heating up, lake surface temperatures are increasing. The stratification, which normally goes from season to season, it changes. It's happening earlier in the year. Because of that, we're getting higher evaporation rates, more algae bloom. And part of the algae bloom is also caused by, again, the runoffs from, say, fertilizer that's put in people's lawns. Declining beach health, agriculture, again, it's affected both positively and negatively, and it depends on the crop. The types of crops actually globally that are being used or can be planted successfully are changing as the climate is changing. Lake ice is declining, but the positive thing about this is that commercial navigation through the Great Lakes, the season can be extended. Lower air and water quality and ground level ozone concentrations are increasing. Part of that goes along with all this is that we're getting invasive species, insects, pests, and plant disease because of the changing climate. Let me give you a couple examples. This one is outside of Michigan. In Colorado, the pine beetle, because Colorado temperatures weren't dropping low enough to kill them off, the pine beetle multiplied and started eating or continued eating more of the trees, which killed the trees, and that combined with the drought accelerated the wildfires. Okay, so let's talk about what we do about climate change. Well, there's three ways we can approach it. One is mitigation, the second adaptation and resilience. Mitigation, you can simply think of it as avoiding the unmanageable. So in other words, we decarbonize our buildings, we add renewable energies, and we look at carbon sequestration, which is just in its infancy right now. Adaptation can be thought of as managing the unavoidable, and several societies, including ASHRAE, REVA, and others, SIPSI, ASME, American Society of Mechanical Engineers, and others, are looking at ways, for example, for buildings to do smart design. Civil engineers, here they are, the American Society for Civil Engineers are looking at ways to do low impact design so that the water is retained in the area and is managed better. We also need to look at resilience, and this is basically maintaining operations while managing a disturbance. For our buildings, we need to provide refuge areas for our people. We need to change the way that we build and retrofit our buildings to protect not only the people, but the building and the operations. So, in conclusion, climate change is real. It's occurring at rates of an order of magnitude faster than the last 20,000 years, with CO2 increasing at 2 orders of magnitude faster since 1960. Today's climate change, I think I've been able to convince you that it's primarily by human activities since the mid-20th century. And we must use strategies to mitigate the changes, to adapt to the changes, and to provide resilience for ourselves and our buildings and our environment. The ASHRAE 2021 Fundamentals Handbook had a new chapter. It's called Climate Change Chapter. I worked on this. I'm actually the chair working on updating it for the 2025 edition of the handbook. It suggests trade-offs between mitigation and adaptation. This is probably one of the most important things to know. Not addressing climate change is expensive, and it's expensive in many ways through loss of lives, extinction of animals and plants, a greater monetary expense. It's bad for our children and our children's children. And who's affected more than anything? The very young or the elderly are the most affected, but the indigenous, the poor, the minority, the nations, the smaller nations, the third world nations are affected more and can't do much about it. So I can't go on after giving you all the bad news without giving you some hope. So yes, we're in crisis, but there's still hope. People are becoming more aware, and one of my goals is to make people more aware that we're in a climate crisis. The cost of renewable energy, especially solar, has extremely deflated in the last decade or so. In fact, today it is less expensive to build a utility level solar plant than it is to do a coal plant. And that is great news. Research is being done and is being developed on ways to capture and sequester carbon dioxide and even to create some green hydrogen. And we need to look at all the ways, not just decarbonizing. We need to look at ways of sequestering also. If we act today, things may not get better, but they shouldn't get worse. So I thank you for your attention, and I hope that I have added your questions. Thank you very much. And I'll turn this back over to Anna Maria.
Thank you, Janice. This was a great presentation, very interesting. I have not seen any chats, any questions in the comments. Costa, have you seen anything that?
Yes, there is one question. I'm hoping more questions will come in. And
okay,
first of all, Professor Means, I would like to thank you for the amazing presentation, but also the compelling evidence that humans are responsible for the climate change. And also for closing with a hopeful message. There is a question from Esan Ibrahimia. The question is, can we dramatically reduce global warming through artificially induced large impact phenomena similar to volcanic activity?
Okay, say I didn't quite understand it.
Can we create artificial large impact phenomena similar to a volcanic activity?
Okay, you're talking
in order
about
to
using
reduce global warming.
There are some theories or some ideas on how to do this. And in my opinion, it's very risky. Okay. The climate chapter does address some of these potential engineering ways of, like ejecting things, for example, into the atmosphere to create more clouds, to create greater albedo, to reflect more of the light, for example. I'm very nervous about them. And let me tell you why. I know that animals have been introduced, for example, in areas, for example, in New Zealand, they introduced, was it raccoons or possums? I can't remember. And it's one of the animals to be able to control another animal. And now they have a problem with the animal that they introduced. And this has happened time after time. So I don't know if we know enough or understand the effects of what our actions would be to try to control climate. I hope that answers your question.
I think, yes, the message was very clear. Also, if I may add to that, there are a lot of technologies that are in the infantry level, and we're having a long way to go, but there are more immediate answers to potentially mitigation and adaptation. And if I may ask here, Professor Mintz, where I'm guessing that most of our participants are coming from the built environment and in the world of buildings. What can we do as immediate steps potentially? And what are potentially, if you can give us a very quick overview of what potentially ASHRAE society is doing in mitigating and adapting to the continuous climate change? Okay,
I'll look at mitigation. We're promoting solar energy and other renewables as TC6.7's mission is. We are also adapting or looking at ways of adapting our buildings. I'm going to be presenting at the winter conference, for example, on how using some of vernacular architecture, that is architecture not done by architects, pre-industrial architecture, which use some natural means, natural techniques to heat and cool buildings. And I think a lot of these have been forgotten. I think those being brought back will help. We also are not looking at necessarily increasing chiller sizes, but things like, instead of doing that, because, well, chillers, for example, HVAC equipment lasts basically 20 or 30 years, or maybe about 30 years. So if we know it's going to be hotter in a particular area, we don't want to install extra oversized equipment for today because it's very inefficient. It uses more energy. So the idea is to install multiple redundant units and leave space for additional ones to go in. So instead of having one large one, for example, we're also recommending looking at where you place your electrical and other equipment. If it's in an area, even in an area that hasn't traditionally had floods, but in areas that may have had floods, you may want to elevate that equipment, not put it in a basement, or take other means to protect it. So there are a lot of ways that we're looking and adapting, and my hope is that we'll have even more listed in the handbook when it comes out in 2025.
Excellent points. And I like what you mentioned, that we don't need to always look on the future to find solutions, because some of the solutions already exist in our past experience. Humans, our species, are very adaptable to the environment. So vernacular architecture can be part of the solution. Jim Laidell has a question here. It says, is anyone forecasting the changing of heating degree days and cooling degree days for the next 10 to 30 years for designers to model as we build new buildings and HVAC systems?
There is some modeling showing what the potential increases for heating degree days and cooling degrees days are. But again, ASHRAE is basically saying be cautious about increasing equipment size and look at other means to cover that potential of increased cooling, basically. Well, the heating degree days are going down, obviously. Cooling are mostly going up.
And also an additional note that depending on the country that you're located, you might be able to find future projections for weather files depending on different climate scenario. I know for sure that European Union, US, and Canada do provide these future weather files for free depending on the temperature increase of 1.5 to 2.5 degrees Celsius for the next 30 to 50 years.
Yes.
So you can also use these weather files to design your future buildings, design our buildings for the future, not for the past.
Yes, and retrofit them for the future too, again, and that's where we talk about resilience.
Excellent point, because I mean, in North America, and I believe in Europe, probably it's even higher, 60 to 70% of our buildings have been reconstructed. That will be present in 2050. So it's a big part of our work that we're not looking into right now. It's only a recent interest that we're looking into retrofitting. Philza Walters has a question here. What specific resources does ASHRAE have on climate education currently and plan? You mentioned the new chapter in Handbook. Could you please give us a little bit more information?
Oh, wow. There are many. ASHRAE is going through a big push for decarbonization of buildings, and there are several publications. Not a couple have actually come out, and they're more in the planning stage. And I don't have their titles at my fingertips, but if you go to ashrae.org and do a search under decarbonization or decarb group. In fact, I think that you might even find it in the list of places to go in the menu. You will see a list of those. Oh, there's so many things that we have published, and most of these are actually, or a lot of them are actually free to the public, so anybody can download them. If you want hard copies, that's another story of buying them. And of course, there are publications and standards coming out, and they have come out, and not only on that, but also looking at indoor air quality, because that is affected, of course, by climate change, especially with wildfires, for example. In fact, that's an area of the new handbook chapter for 2025 that we're going to elaborate on. Sorry, I don't have a list in front of me. I wasn't prepared to answer that. Although I have given talks or presentations on all of the educational publications that ASHRAE has on this, and there are many. So please go and explore. And if you send me an email, I'll try to be more specific. It's jmeans@ltu.edu. Thank you.
As you said, there are several resources within ASHRAE. Also, ASHRAE has several task forces that directly or indirectly address climate change, mitigation, adaptation, and resilience. And interestingly enough, for the past 4 or 5 years, ASHRAE is trying to reflect a lot of these aspects into the existing handbooks and standards. So there's a lot of work that has been published. Some of it is publicly available for free. Some of them, of course, you have to be an ASHRAE member or pay for it. And there is even more coming out. Also, there are several, if you have a look into the current, a little note here, the upcoming ASHRAE conference in Chicago on January 20 to 24th, you will see that there are several sessions, including the one that Professor Means is presenting that are dealing with climate change, directly and indirectly. Are there any other questions? If not, yes, please.
I'd like to add one more thing, especially for TC 6.7, which is the sponsor of this, but also TC 2.5, which is the climate change technical committee, and also 2.H, which is sustainability in meetings. But for any TC, anyone can attend meetings You don't have to be a member. You do not have to register for a conference. And since the pandemic, we've had many online meetings. So that really opens it up to a lot of people. And I just wanted to put that plug in.
Excellent closing point. That there is the ASHRAE conference, but we also have the technical committee meetings that are open to the public. I highly recommend to whoever wants to join in person or remotely, at least for our TC6.7, to join our TC6.7 as a member, so we can keep you up to date and inform you when the next meetings will be coming up. And of course, if there are other TCs that are interested to your work, feel free to join similar links. Professor Mintz, we would like to thank you for taking the time to present that amazing evidence. Sometimes it gets overwhelming for us as professionals in what we have to deal with in the biggest challenge and crisis that we have faced as a humanity, but I'm also happy to see a positive energy and intention, and there is a lot of work for us to do. And a little note for our participants, we'll be following Professor Min's presentation with new webinars that will be complementary to the work that Professor Min's presented today. So we'll be building up related to webinars to TC6.7, which is solar energy and other renewables. At the same time, we'll be sharing with you the recorded presentation, and we'll be posting it in our website, the 6.7. Also, you can follow us in LinkedIn, and we'll be posting the presentation in YouTube for the public. Professor Mintz, thank you on behalf of TC6.7, and thank you everyone for joining us today's session. And of course, our outreach committee chair, Ana Maria Sigunis, thank you for organizing all that, and of course, Kostas Balaras and Khalid Negiri for coming up with the idea in collaboration with Professor Mintz.
Thank you for this opportunity, and I hope all of you stay safe and that you use this knowledge positively. Thank you.
Have a great rest of your week.
Bye now.